Hello, we're going to talk about topic 1.5, and we're going to take a look at limits using algebraic properties. Okay, you're going to see that a lot of these properties are just ways we can expand limit expressions. So I'm going to kind of go through these one by one. The first one, sum difference property. Now I have addition on here, but this works the same for subtraction as well. If you have a limit of two functions, okay, and those two functions are being added or subtracted, you can actually separate those two limits. I'm sorry, you can separate that expression into two completely different limits. That works for subtraction. Scalar multiple property. If you have a constant multiplier, so any real number value, we can take that real number value and we can take it to the outside of the limit and just figure out the limit of the function itself and then multiply it by the constant at the end. Product property, similar to addition and subtraction. If you have a limit of a product of two things, you can separate it into a product of two different limits. Quotient property, now this is a big one. This is one that College Board really scrutinizes. So if you have a limit of a quotient, we need to make sure we split that quotient up into two different limits and then evaluate. So that's going to play a role in some stuff we're going to do later. So for these notes, we're going to take really good care, and we're going to make sure we write proper notation for all those quotients. Last but not least, power property. If you have a function raised to an exponent, that exponent can then come outside the limit, and we can just raise the output of a limit to that same power. We'll get the same answer. Okay, so let's take a look. So I have an example with two graphs, f of x and g of x. Okay, and I want to apply those properties to the following, I think there's 6 limit expressions. Okay, so we're going to start with part A, the limit as x approaches 2 of f of x and g of x. And all we're going to do to start here is we are going to expand this. So I'm going to say the limit as x approaches 2. If my stylus would work here, we'll get it working. There we go. Okay, of f of x plus the limit as x approaches 2 of g of x. And now I can just evaluate these two limits separately. So if I find the limit as x approaches 2 for f of x, that's going to wind up being this little hole. If I can write, there we go. This little hole here at the top. So that's going to be at a y value of 2. And then I'm going to do the same thing for g of x as x approaches 2 for g of x. So as I approach 2 from the left and from the right, that's going to give me a y value of 0, which if I do 2 plus 0 gives me an answer of 2. Okay, so we're going to do all these using those properties. So for part B, let's practice expanding it first. So the limit as x approaches 1. There we go. Of 2 f of x minus the limit as x approaches 1 of 3 g of x. And I can take those coefficients out. And let's see what we get here. So now if I evaluate the limit as x approaches 1 of f of x, so let's erase some of the markings I have up here. So I'm going to now where x approaches 1, which is going to be a y value of 1. So I'll be 2 times 1 minus 3 times g of x at 1. Now, if you notice, for g of x, the left and right-handed limits are not going to the same values. So that limit does not exist. So since one of those limits doesn't exist, we can make the conclusion that the entire question or the entire limit expression will not have an output. Okay, so next we are going to do a product. So again, if I expand this out, I have the limit as x approaches 0 of f of x times the limit as x approaches 0 of g of x. And let's erase a bunch of these little markings here so we don't get confused. So let's get rid of g of x as well. Okay, so now if I go to 0 from the left and from the right, that's going to give me an output of 0. And g of x at 0 is going to be this y-intercept. Now, I don't really know exactly where that y-intercept is. Let's call that b, for instance. I do know that it's a value, and I'm going to multiply it by 0. So it really doesn't matter in this problem what it is, because 0 times anything is 0. That would be the output of my limit. Okay? For part D, we have a quotient. So let's go back. I'm going to say the limit as x approaches. So write it all out. Practice your limit statements. -1 of f of x all over the limit as x approaches -1 of g of x. Now, when I do this, if I check -1 for f, so -1 is going to be at -1. Over, and let's see what this bottom is equal to. So g at -1 is also going to be 0. Now, if you have the fraction of -1 over 0 or any constant over 0, that's undefined. So this limit does not exist. Okay. So let's go over to the next one. So I have another product. So I'm going to say the limit as x approaches 1 of x cubed times the limit as x approaches 1 of f of x. Now you could use a power rule on this first piece. I don't really need to. 1 to the power of 3 is just going to be 1. However, I do want to evaluate the limit as x approaches 1 of f of x. And if I do that, so as x approaches 1, it's going to be this point. So it's going to be at 1. And 1 times 1 gives me 1 as an answer. All right. Now, for part F, we have what we call a composition of functions for part F. We're going to skip this for right now because on a later page of these notes, we're going to do a whole bunch of compositions. So for right now, you can just skip part F. All right. Let's do 3 more. I think it's 3 more. Yep, 3 more. Feel free to pause the video if you want to try to do these 3 on your own. Okay. See what you get, and then, of course, unpause and check your work as you go. So I'm going to go through these one by one. If I were to start and expand this out, again, practicing proper limit notation, limit as x approaches -1, and we're going from the left of f of x plus the limit as x approaches a -1 from the left of g of x. If I do, as I approach -1 from the left of f of x, that's going to be at 0. And as I approach -1 from the left of g of x, sorry, the last one was f of x. This one's g of x is going to be at a -3. So if I add those together, I get -3 as my answer. Part B, if I do the limit as x approaches 1 from the right, so again, just practicing good notation. I know writing these limits is a little cumbersome sometimes, but I really want to build good habits. So I can take this limit and then I can square it. So if I do g of x as x approaches 1 from the right, that's going to be the constant function that's on the right-hand side. So that's going to be a value of 3 squared, which gives you 9. And then part C, I have a quotient. So we talked about this. AP is kind of strict on their quotients. I want the limit as x approaches -2 of f of x all over the limit as x approaches -2 of g of x. If I check -2 for f, that's going to be the top of this little quadratic here. So that's going to be at a value of 1. And then if I check g of x at -2, that's going to be at a value of -3. So I get the answer of -1/3. Okay. All right. Compositions. Okay, so this is when I have one function substituted into another. Now we're going to use the same graphs for these. So I didn't give you the equation. So this is very difficult to do at, without an equation. You have to kind of process, what's going where. And the first three problems I have, we're going to talk about, as long as there's continuity, right? So continuity is very, very important when we're doing compositions. You're going to see the way I approach these three is slightly different than the way I approach the next three. So, so when I do this, I'm going to kind of show you my thought process here. I want you to follow this pattern. As x approaches -3 of g of f of x, that's going to be the same thing as saying the limit as x approaches. Now I'm going to pause. Now if you notice, the input of g is f of x. So I'm going to start from the inside out. So if I take a look at f of x, as x approaches -3, now this is a two-sided limit. So let's erase all these little notations here, all these little arrows, because I don't want to get confused. Help if my stylus worked. Okay, so as I approach -3 from both sides for f, okay, you can see that from both sides, I'm going to be at a value of 0. So the way that I'm going to write this is now the limit as x approaches 0 of the outside function g of x. So again, the input of the original problem was f of x, and we evaluated that limit. So now the input is going to be 0 of g of x. And if I evaluate this two-sided limit, so the limit as x approaches 0. Now again, two-sided limit, g of x at 0. So from the left and from the right, that is going to give me an output of -1. Okay? So let's do that 2 more times. All right? I want you to see along with me. If I take the limit as x approaches -1 of f of g of x, so that's the original problem, this is going to become the limit as x approaches -1. Oh, sorry. We don't know that yet. We need to figure out what that new input is. So if I approach -1, starting from the inside, so g of x at -1, so I'm going to come up here. And at -1, we're going to the value of -3. So as x approaches -3 of the outer function, which is f of x, so now I just need to evaluate that limit as that two-sided limit as x approaches -3 of f of x, and that's going to end up being my 0. Okay? So one more. All right, I got my notes here, so bear with me. All right, if I do the limit as x approaches 4 of f of x, that's the same thing as saying the limit as x approaches. Now the inner function is f, so as I approach 4 from both sides, so that's over here, that's going to go to 0. So that's going to be my new input of the outer function, which also happens to be f. And then if you evaluate the limit as x approaches 0 of f of x, it's going to be right here, two-sided limit. That's going to give me an output of 1. And that'll be my answer. Okay? So now I kind of put in a blue box here. A key component of a limit of a composition of functions is that f is continuous at the value the limit as x approaches c of g of x. So what that means is if you don't have continuity, then we need to take a little bit more care, right? So if you take a look at -2, for instance, what we're going to do is we're going to break this up, and I want to kind of show you an issue that we have. So I'm going to start in red here, and if I do this, this is going to become the limit as x approaches -2 of g of f of x. Now at -2 of f, if I go to -2, if I take a look at this, this is going to give me a value of 1 of g of x. But now if you try to evaluate g of x at 1, you're going to see that there's a discontinuity here, and that's not good for us. Now, this question does have an answer. I don't want you to think that this doesn't exist, because there's something very, very tricky here. As I approach, so if I go back, and as I approach -2 from both the left and right-hand side, I'm getting to a value of 1. But do you notice how, like, as I get closer to -2 on the left-hand side here, it's getting, it's less than 1, but getting bigger. It's getting like 0.9, 0.999, 0.9999. And the same thing's happening from the right. Because this is a maximum, okay, I know all the values leading up to it on either side are going to be less than the value of 1. So what that means is it means that this piece here is going to be getting closer and closer to 1, but from underneath, from smaller and smaller values, okay? So this gives me a one-sided limit for g of x, and that one-sided limit, so as I approach 1 from the left, is going to be this value, and I apologize, I should probably have a point here. I should also tell you where that point is, but we're going to assume that that's going to be at 1/2, okay? So it's going to be at some decimal between 0 and 1. I'm pretty sure it's at 1/2 is how the equation was originally written, all right? So we're going to do that again, because I know that's a lot, and the first time I go through it, it's a little overwhelming. So if I do this again, so the limit of f of x. So if I go through this, come on. There we go. All right. So I'm going to now have the limit as x approaches. So as I get closer and closer to 2 for f, so here and here, I'm going to a value of 1. All right. Now you can already see we're going to run into the same problem that we had on last time, because we already know that there's some issues as we get closer and closer to 1. But what I want you to notice is that as I go from the left and I go from the right, this is a minimum here, which means all the values to the left and to the right of 1 are bigger, which means I'm coming from it from larger values, which ultimately means from the bigger values or from the right-hand side. And what that gives me is as I approach 1 from the right, from f of x, it's going to now be, if you look at this graph, as I approach 1 from the right, it's going to be the value of 2. Okay? And let's do one last one, very similar. Change colors here. The limit as x approaches, now as I go to 3, what's f getting closer and closer to? Let me erase all these little things here. So as I approach 3, you can see I'm getting closer and closer to the value of 1. Now, I do want you to see, though, as I get closer and closer to 3, from the left, I'm on the upper side, and from the right, I'm on the lower side, right? So when I do this, this doesn't have a direction. It's got to be a two-sided limit. And because it's a two-sided limit, when I now go to 1 from either side, those aren't going to be the same from the left and from the right. So if that's the case, then this does not exist. Okay, so that is my limit for certain compositions. Now, this is a very specific style of problem. I saw it in one of the AP conferences that I've been at. So when you have a composition of functions that's not continuous at a point, we have to see if it's supposed to have a direction on that limit or not. And normally that comes from when you have maximums and minimums. So we'll kind of go from there. All right. So that is all of topic 1.5, properties of limits. Hopefully this helped you, and you can complete any further tasks.